All right, question 4. Materials question. In the production of steel alloy, atoms of carbon are added to iron. The resulting alloy is less ductile than pure iron. State the meaning of the term ductile. Sorry about the creaking. I really do need a new office chair. State the meaning of the term ductile and describe on an atomic scale why the addition of carbon atoms can make steel less ductile than iron. Okay, so first up, what does ductile mean? It means able to undergo a large plastic deformation. You'll sometimes see it defined as able to be drawn into wires. I believe that traditionally was its definition. But if something is able to be drawn into a wire, it has to be able to undergo a large amount of plastic deformation. Why does the addition of carbon atoms make the steel less ductile? So carbon atoms, the key thing here, this is only a 2-mark answer, and I feel we've already got the first one. So, we're not looking to go into a great deal of detail here. We need to say the most fundamental reason for this. Remember that plastic deformation is able to happen in a crystalline substance because edge dislocations can move through that substance. The presence of foreign atoms prevents or inhibits that motion of edge dislocations. So that is overwhelmingly the most important thing to say here for this second mark. Either prevent or inhibit or hinder. So that movement of edge dislocations is absolutely crucial to plastic deformation. It basically cannot happen without that. Okay, part B. 2 wires, one of steel, one of copper, same length L/2, each with the same cross-sectional area, attached end to end, suspended from a support, and a force F is applied as shown. So the diagram here shows us our copper at L/2, our steel of the same length, and we're going to apply some force F. Equal cross-sectional area. The strain energy in the wire combination due to the stretching force can be given by this, a half of x times change in length. That's pretty standard, where delta x represents the total extension in the wire combination. Show that this must be true. Okay, I think we can do that. So I think the starting point here is to suggest that this total extension represents the sum of the extension of the copper. It's going to extend by xc, I'll call it, and the steel is going to extend by xs. So I think my opening gambit would be to suggest that the change in length is equal to the sum of extension of copper plus extension of steel. Then we're going to have to come up with an expression for each of these. So Young modulus, generally, stress over strain, that is equal to force over area divided by extension over length, which is equal to FL over AX. So therefore, X is equal to FL divided by A times E, and X copper must be equal to F, the original length, L/2, divided by the cross-sectional area, where is it? Cross-sectional area is just A, multiplied by Young modulus for copper. So therefore XC equals FL over 2AEC. And I think we could just go ahead and state that by the same rationale, the extension of steel must also be equal to FL over 2A ES. Bearing in mind they're both under the same tension. The copper is supporting the steel, it must be carrying the same load. Okay, from this point then, we're told that the work done when we extend this wire is a half of F times delta X equals a half of F multiplied by XC plus XS. Oops. And then all we have to do surely is sub in these expressions that we found, and hopefully what comes out looks like what we've been asked to find. Yeah, that's going to be fine, isn't it? So I think I can just, how many marks? 3 marks. I think it's okay to do this then in a single step. Yeah, we're going to have F squared in front. We're going to have L in front. We're going to have 4A on the bottom. 1 over EC plus 1 over ES. Okay. So really the crux of that was just recognizing that the total extension is the sum of the two, and then just subbing in an expression for each individual extension. Calculate W when F is equal to that, A is equal to that, L is equal to that. So this is very much just put the numbers into the formula. I don't see, yeah, it doesn't seem to be much to this really for 2 marks. So 45 squared multiplied, just check the units in a question like this, you know, just make sure the units are what you're expecting. I mean, not just a question like this, that is always a good thing to look for. Just make sure the units are what you think they are. You know, this cross-sectional area is in square meters, but it's just always worth double checking that sort of thing, because those are easy marks to throw away. So F squared times L over 4A, and that's going to be multiplied by 1 over, these are gigapascals, so times 10 to the 9. And that is very much a job for the calculator. Yeah, slightly odd question. Okay, 0.045. And this is an amount of work done, so the units here, joules, capital J. Yeah, a little curious about that one. It doesn't seem very taxing. You know, you're given a formula and then it basically gives you values for all the letters and you're subbing them in. So 2 marks, maybe there's a unit mark for that. I'm not sure. I'm not sure why you get 2 for that. Okay, a student measures total extension of the combination to be approximately 2 mil when F is 45 newtons. Determine whether or not the measurement is consistent with your answer to BII. It was 45 newtons last time, so arguably the quickest way to do this is just to determine whether the amount of work done here matches what we've previously calculated. So this time half times slightly simpler. Again, just always careful with the units. This is 2 millimeters. And that is exactly 0.045 joules. So yes, it is consistent. Oops. No problem. Okay. Oops. Jasmine wishes to determine the Young modulus of the metal. In the form of a wire, she makes the following measurements with uncertainties. Okay. Determine the Young modulus of the metal along with the absolute, and look, it's in bold, the absolute uncertainty. Give your answer to an appropriate number of significant figures. So, a couple of things here. What we're going to have to do is, whatever calculations happening here, we're multiplying together several values, dividing. So we're going to need to turn these into percentages so that we can then add the percentages. We need percentages. The next thing that we'll need to do is actually calculate the Young modulus, apply our total percentage uncertainty to it to turn it into an absolute, and then we'll think about significant figures. As a reasonable rule, an absolute uncertainty should not be more than one significant figure, just as a fairly general rule. So let's do this. I will start by just calculating the actual Young modulus. So remember, it's stress over strain, which is equal to FL over AX. So in this case, tension 7.8 multiplied by initial length 2.825 divided by so for the diameter, this is in the form of a wire, and if it's a wire, we assume that it's a circular cross section. So pi r squared is going to give us the cross-sectional area, so just be a little bit careful, especially with the units and such here. Oh, sometimes my pen thinks I'm trying to draw ships, and it very helpfully turns that into a triangle for me, but actually it was a 3. So this diameter is in millimeters, so just being a bit careful, and obviously we need to half that to turn it into a radius, and we need to square it and multiply it by pi to turn it into an area. So that's my cross-sectional area, this this bit. That's the cross-sectional area. Multiplied by x, the extension, 1.8, again, careful with the units, times 10 to the minus 3 meters. So I'll chuck that all in the calculator. I do not fancy that one in my head. And I'm expecting, where it's a metal, so I'm expecting something in the region of 100 gigapascals. And the answer I've got is 1.522 times 10 to the 11 pascals. So that is 152 gigapascals. So we're in the right sort of ballpark. It's always worth having that in mind when you're calculating something like this, because you do frequently have a calculation with a lot of powers of 10 flying about. So it's always worth thinking to yourself, does my answer seem reasonable? Hundreds of gigapascals for the Young modulus of a metal certainly is reasonable. So now for the uncertainties. So let's find the percentage uncertainties in everything, basically, because in this equation that we've used, everything, there's nothing added, everything is multiplied or divided, so we need to sum the percentage uncertainties. So percentage uncertainties in D, 0.01 over 0.32 times 100%. 3.125 Therefore, the percentage uncertainty in area is going to be 2 times that. And remember, when we square something, we're multiplying it by itself. And if you multiply it by itself, then you add the percentage uncertainties. So we're adding 3.125 to itself to get 6.25%. Okay, initial length 0.005. This is going to be very small. Okay. 0.18%. So pretty tiny. And what's next? Force. (0.1 over 7.8). 1.3%. 1.28%. And finally, extension 0.2 over 1.8. (11.1%). 11.11%. Okay, so in my equation, FL over AX, I've got FL, A, and X. So this one, this one, this one, and this one. I need to sum these. To give me the percentage uncertainty in the Young modulus. So 6.25 plus 0.18 plus 1.28 plus 11.11. (18.8%). And then I need to turn that into an absolute. The absolute uncertainty in that Young modulus is just equal to 18.82 over 100 multiplied by the value that we've already found. So 1.522 times 10 to the 11. Which gives me, well, it's 2.86 times 10 to the 10, but I'm going to write it as 0.286 times 10 to the 11, rather than as 2.86 times 10 to the 10. And the reason I do that is it's really helpful to have the same exponent here as I've got in my actual value. So my final answer then, I'm going to write it down with all the significant figures and then sort of talk very briefly about how to adjust that. If I have them both to the same power of 10, then I can write it like this: 1.522 plus or minus 0.286. I can just stick a bracket there and say that that is multiplied by 10 to the 11. But can't leave it like this. So as I mentioned, absolute uncertainties, one significant figure. So change that to 1. And once you've done that, then your value should match the decimal places. So, these are meaningless on the end when I've got an uncertainty of 0.3. Those just don't have any meaning. So we'll get rid of those to leave 1.5. So 1.5 plus or minus 0.3 times 10 to the 11 pascals. Desmond repeats the experiment using a wire made of the same metal original length, but with a larger diameter without further calculation. Discuss how this change might affect the uncertainty in her result. There's quite a lot of marks for this, 4-mark response. So 4 points to be made here. So let's go back up. If we use a larger diameter, if we go back and look at this, this diameter has been measured to a resolution of 0.01. So if we use a larger diameter, we will decrease the percentage uncertainty in the diameter. So that'd be the first thing to say. That's going to make quite a significant difference then to cross-sectional area, because the cross-sectional area is double the percentage uncertainty. Whoops. So we'll get a significant decrease in that. So there's 2 marks or 2 points that I've made so far. I definitely need to say more. Why is this a 4-mark question? What are we missing here? In general, if you increase the size of the thing you're measuring with a given piece of equipment, you reduce the percentage uncertainty, and that seems like a good thing. But if we look at this equation, since we're not changing F, we're not changing L, and we can't do anything about E, if we double the diameter, for example, that is 4 times the cross-sectional area. Therefore, the extension that we will experience will be 4 times smaller. So that is going to be a significantly smaller extension. So therefore, smaller extension implies larger percentage uncertainty in extension. And if we look at these results, that is actually the bigger factor, the percentage uncertainty in the extension. And I think that's probably enough. And that's my doorbell ringing, so it is going to have to be enough.